All right, we're back with video 2 for inverse trig integration. Again, whenever you're starting a new problem, inverse trig is not your first guess, right? You would look at this and say, well, is there something I can do just simply, right? But unfortunately, we can't simplify this denominator. It's in the denominator. It's not going to work with power rule, things like that. A u substitution would generate more e to the 2x's, and I only have the 1 underneath. This one is a little tricky maybe to see the pattern, but it is actually going to be an APCalc problem. The piece that you need to notice is that this piece here, right, e to the 2x is actually e to the x quantity squared, right? Power to a power, you multiply, right? So e to the 2x is a perfect square, just like x squared would be. So the substitution that we're going to want to set up is that our u is e to the x. Now the trick here, though, is that my derivative then would also be e to the x. And then I'm going to break my own rule about mixing my variables. Right? If you look at the top, I do not have an e to the 2x in the numerator to work with. So it looks like at first glance that maybe I've sort of done a substitution that isn't going to help me out. The part that is the benefit here, though, is that my e to the x, if I divide it over, well, it's precisely the same as my u value. So I could express dx solely in terms of u. Okay, we wouldn't be able to solve if we had mixed variables, but because I can go back and use that substitution again, I can express dx solely in terms of u. So let's go back and rewrite. We're going to take that dx on top, and instead of pulling our over u out front, because we can't, right? It's not a constant. It has to stay in the problem. It'll be our 1 over u, and then du. So that dx became 1 over u du. And then underneath, right, I would have the square root of u squared minus 1. That is exactly the same as my APCalc pattern, right? You might be wondering where the absolute values went, right, from before. They're not actually in our formula. If we look at the front side, you don't have to have the absolute value here. Right? It doesn't have it, but the derivative did. And it is working out here because our e to the x is always positive. So the absolute values are sort of a moot point. But now, right, it's that perfect pattern, and I can go ahead and I can say that this would be equal to the APCalc, or secant inverse, of u. And we'll throw on our plus c. And I'm all set. The hardest part about that one is recognizing that it is indeed the pattern for inverse trig. All right, we've got another one. And here you can see my heading, rewriting as the sum of two quotients. If I look at this problem again, your first choice is never just to jump to inverse trig. But if you tried something like a u substitution, the problem would be that you'd have this 2x. Well, I could deal with 2x du or dx, but I wouldn't be able to cope with the plus 2. So the trick to this one is that I want to go ahead and split up that sum. You can split a numerator, so we'll call this one x over the square root of 4 minus x squared, and we'll add on our 2 over the square root of 4 minus x squared. Right? I haven't actually changed the problem. I've just written it in a way that's going to be more convenient. And in reality, this first one doesn't even belong in this section. I'm not going to jump to inverse trig. I'm going to look at this and go, oh, well, u is 4 minus x squared. So du is minus 2x dx. I have an x dx. And so the only thing I need to do is divide out the negative 2. If I'm using that as my substitution, then everything circled in green becomes negative 1/2 du. And I would have u to the minus 1/2. That's just a nice, simple power rule, right? We don't want to overcomplicate everything. You still have your old rules. So I will get negative 1/2, u to the positive 1/2. If I divide by that positive 1/2, I'm going to actually have a multiplier of 2. And so 1/2 times 2, I get negative square root and 4 minus x squared. So that first piece did not require inverse trig at all. It was a nice, simple u substitution. Now here, right, this is a perfect example. I wouldn't be able to deal with the x2x. I wouldn't be able to do anything with that 2 because it's related to the x, or it's not related to the x that's here. But if I notice, right, this is my arcsine pattern, right? The 2 is just a constant multiplier. My a is a perfect square, right? 2 squared is 4. And again, my u is a nice simple x. So I don't need to fully go through with a u substitution here. It's just a matter of naming because there's no multiplier. And so this part, I can just jump straight to my solution piece. The 2 here is, again, from that numerator. It's just a scalar multiplier. And the integral of 1 over the square root of 4 minus x squared would come out to be the arcsine of x over 2 plus c. So oftentimes, you end up having to split and then showing and carrying out 2 separate integration processes. For those of you who are moving on, this will come up a lot next year in BC. All right, our next example, completing the square. We want to make those perfect squares, right? If you just tried to use u substitution, maybe you're thinking logarithms, use the denominator, right? You're going to generate 2x minus 4. There's nothing I can do with that in the numerator. So how can I force this thing, think of it that way, to become a perfect square and to take on that pattern? Well, you have this method of completing the square that we worked on in pre-calc. So I'm going to go ahead and I'm going to think about how to complete the square and sort of force inverse trig on this problem. I'll have x squared minus 4x, and I'm going to keep my plus 7 off to the side. With complete the square, the constant wants to stay on its own. I take that middle term, and I'm going to cut it in half, and then I square it. So I have a negative 2 squared. Now, I've added it. I like to do mine in a different color to point out that I am changing the original problem, right? So here I've technically added 4 units. I've added a 4. So I need to go ahead and subtract 4 so that the overall balance here would be a 0. I've had the net gain of 0. And if I multiplied this out and simplified, I'd be right back where I came from. The benefit to doing this extra step then is that I can take a problem that was previously unsolvable and I can rewrite it in a way that's going to work. Right, so far I just simplified. Well, now I have a quantity that's being squared. This is my variable, u equals x minus 2. We're in luck, right? Our du and our dx are one and the same. So it's almost like a naming convention here. And my a, right? Everything's really a perfect square if you just throw a square root on top. So overall, my answer then would be that I would have 1 over the root 3. I'm looking at my formula, right? 1 over a. Arctan. Let's use tan inverse, it's faster. And then I use u over a. Right, so I didn't have a way to start this problem, but I could force the inverse trig on it by using that complete the square process. I think I'm going to have to make a third video to make everything fit, but example 4 will continue in just a moment.